I learn best by seeing how it's used in practice. Let's talk about MP3 encoding. There's a lot of tricks used in MP3 encoding, but at its most fundamental level, it takes a continuous time signal, x of t, and it puts it through an A to D converter, where we've got some sort of sampling function here, and that converts it to an x of n. And our x of n okay, so the idea is that I've written it in a matrix, just to partially to save space. And that matrix loops around like this. And that's great. We've got this x of n, and a typical f of s is at 44.1 kilohertz. So every second of recording, we have 44,100 samples, and that's a lot. We want to be able to somehow cut that down. So we're going to throw that into a DFT. And what this gives out is our x of k. And that means that now we've got, when we throw it into our DFT, what we're really going to do is throw in one set of values up here, one row, followed by another row, and followed by another row. So our first row of values will give us a same length row of numbers. I'm just going to represent them by dots since I'm running out of room. And then this is going to give us the same length row of numbers, and this is going to give us the same length row of numbers. And so far, great. We have not accomplished anything. We've just changed one set of, for a 1 second recording, one set of 44,100 numbers for a different set of 44,100 numbers. Each set corresponds between 0 and 2 pi. We know that this half is extraneous. So we've now cut down from 44,100 numbers to 22,050 numbers. But then we can have a variable cutoff. The fact is that this will allow us to encode sounds up to, what's our highest frequency that this will let us hit, Kevin?
It's 88.2.
The other way. It goes the other way.
22.05. I'm not.
Yeah.
Okay.
That's it. Yeah. So if we sample at FS, the highest frequency that we can unambiguously record it at, aliasing is half that. Most music sounds, most vocal sounds don't have any kind of interesting sounds up in that range. I can't hear 22 kilohertz. I don't know if I could ever hear 22 kilohertz. I'm not sure if you could. You could hear 20 kilohertz. I can't. The highest sound that I could possibly hear is probably about 16 kilohertz at my age. So a lot of this upper stuff is just wasted. Furthermore, even if you hear 16 kilohertz, it's not going to sound musical. It's not going to sound interesting. It's not going to add anything to it. It's going to sound like the most impossibly high-pitched whistling sound that you could possibly hear. We can actually cut off more of this. And depending upon what is being said, if it's a quiet sound in the symphony, there's no reason to encode a lot of high sounds because there are no sounds. If it's a very busy sound with lots of cymbal crashes with a lot of high sounds, maybe that one will want to have a lot of there's a lot of high frequency content. These numbers are over here are high, so we push off our cutoff up high. Next one is maybe just instrumentals, and maybe it's a lot of cellos. So it's got some higher harmonics, but not nearly as high as cymbal crashes. And so now for every row in our time domain, we can encode it with a variable frequency cutoff. And now we can really cut down how much information we're processing. So after we process it, we might cut it down to 10% of our original set of samples. Does that make sense to everyone?
Sir, so what you're saying is the cutoff at pi could be as low as like pi over 4 if need be. Okay.
Or lower if it's a quiet section in the symphony, in the whatever you're listening to. Absolutely. Think about as we're talking here, how much time am I paused? for that, we could cut down omega all the way down to 0. Even when I'm talking, my fundamental frequency is probably about 400 hertz or so, but I don't have anything higher than about 4 kilohertz in my voice. You could cut me off with a hard filter at 4 kilohertz, and not only would I be perfectly understandable, you wouldn't be able to tell the difference. Your telephone conversations on your cell phones are all cut off at 4 kilohertz to enable more cell phone conversations to fit on the available bandwidth, and you really can't tell that those sound poor. There's a lot of other tricks with MP3 working. Obviously, then you have to figure out how many of these samples in each row are being sent, and there's some neat ways to code it using Hammond coding that makes it even more compact. But that's at its core, it's a DFT problem. Okay. Any questions about any of this?
So I have a more general question.
Shoot.
So all these examples, when we're working with the DFT and DTFT, all these are like complex outputs.
Yes.
We've only really been talking about the magnitude. And so
That's right.
do you care about the phase values as well, or no?
Yeah, that's a really good point. So we've got this x of k, which in general is equal to a magnitude component times with a phase angle of the angle of x of k. There are times that we care a lot about the phase angle, and there's times that we don't care at all about the magnitude. It turns out that you hear magnitudes. You don't hear phases as much. If there's a high and low frequency that you hear, the relative phases don't match much. So if it's an auditory thing, we care primarily about magnitudes.